Well,
They're muted, right? So
No, yeah, no, we're muted. Yeah, they don't hear us.
can you hear me in Brownsville?
No, you're muted. That little flashing around the touch panel, bottom right on the touch panel, flashing microphone.
Okay.
There.
Okay, can you hear me in Brownsville?
Yes.
Okay, good.
Can you hear it?
Yeah, I got you. Okay, good. So what I'm going to do, I got tired of typing out PowerPoint slides and, trying to maneuver with, the transitions and stuff. I'm done with that. Okay. So what I'm going to do is I'm going to use handwritten notes that I have from a few years ago, the first time I taught this class, and I'll just project them up here. I've put them in the Dropbox. Okay. So this set of notes and the next set of notes are in the Dropbox. Okay. So don't worry about the lecture number 40 or number 41, so on and so forth. Okay. And there'll be some other points where I'm referencing, other times in the semester. And if it doesn't make sense, don't worry about it because it's, like I said, it's from a few years ago. And then the other thing I wanted to tell you is that I don't know if you noticed, I put the homework in the Dropbox as well. Okay. So if you have questions about the homework, just let me know. But it's dealing with some computations on the Klein-Gordon field and the annihilation and creation operators. I think constructing the Hamiltonian. Some of those places where I told you there were going to be homework problems.
you're serious about it.
Yes. Just wait till you see these notes, man. I must have been a hard ass back in the day because I assigned some hard homework. Anyways, all right. So what I want to do today is I want to eventually get to the Dirac equation. So an equation for a spin 1/2 field. So far we've just talked about scalars, right? Even last semester we only talked about scalars. We never really talked about particles that have spin. Whether it be spin 1/2 or vector particles like photons. Okay, so we want to start real quick, with a quick review about what we mean when we say that an equation is relativistically invariant or Lorentz invariant, and then we'll talk about that in context of a scalar field, but then we'll talk about how you generalize that to vector fields and any other representations of what we'll come to know as the Lorentz group. In other words, this group of transformations on different types of fields. Okay? So let's start by just considering, again, our scalar field, right? Or it could be just a collection of fields. And let's say we have some operator D. Okay, so I'm starting at the basics. Okay, so D is just some operator. It could be the Klein-Gordon operator. It could be whatever operator you want. Okay? And in one reference frame, when you apply this D operator to the field, you get 0. Okay? So we say that an equation is relativistically invariant or Lorentz invariant if, after I do a Lorentz transformation, whether it be a boost, rotation, or some combination of those two, if I get back the same form, right? If the transformed field obeys the same equation, then we say that equation is relativistically invariant or Lorentz invariant. Okay, and those are the types of equations that we're after because one of our things, we're not only trying to describe quantum systems, but we're trying to describe relativistic quantum systems. Okay, so we want them to be Lorentz invariant. Okay. And one thing we've talked about, and I think during the summer we saw this explicitly, is that working in the Lagrangian formulation of field theory as opposed to the Hamiltonian formulation is really nice. It's particularly easy to discuss Lorentz invariant because the Lagrangian is a Lorentz scalar. Right? And the thing that you know about a scalar is you can perform Lorentz transformations all day long and it's not going to change. Okay? So that's why we typically work with the Lagrangian. Right. Okay. All right. So let's get down to basics. Okay. So let's talk about a Lorentz transformation of some space-time point. Okay. So I'm making a transformation from x, some x frame to an x prime frame. Right. And we're doing this in Minkowski space-time. Okay. And so the way we formulate this is by taking a transformation matrix, this 4x4 matrix, Lorentz transformation matrix, and operate on our original space-time point, right? And that gives us a new space-time point, okay? But what happens to the field under this transformation? When we do a Lorentz transformation of a field, what are we actually doing, okay? And the way to answer that question is to think about the field as being some distribution in space-time, right? So it's distributed over space-time. So this is, I've drawn kind of a cartoon. I'm calling this field space, okay? So in field space, this is what our field would look like, okay? And it will have some minima and maxima, okay? So I'm just denoting one maxima denoted at x naught, okay, within that field. Right? And let's say we perform a transformation, a Lorentz transformation of this thing, okay? So the new distribution, right, so that we know how space-time points transform, right? So the new distribution, wherever it goes, or wherever it's, we transform it to, the new point, or the new maxima is going to occur at the transformation of our original maxima. Right? So I'm denoting x here as our new maximum, and it's just the Lorentz transformation of the original maximum. Okay, so in my little cartoon world, this is what my transformation of my field looks like. Okay, so I'm performing some boost, some rotation, whatever. Okay, and mathematically we would write the field down. We've done this before. But the field under Lorentz transformation goes to some phi prime field, right? And that's equivalent to the original, just the field itself with the space-time arguments transformed. Okay. All right. So we know how the field transforms. Okay. So let's talk about, in particular, the Klein-Gordon equation, or the Klein-Gordon theory, right? And let's see if the Klein-Gordon Lagrangian remains unchanged under a Lorentz transformation. And I think we've done this probably 5 times, but just bear with me, okay? Because it's a good build-up to what we're going to talk about. Okay, so obviously the mass term is going to just be transformed like the field, so it's just going to be transformed to some new space-time point, right? The field's going to keep its shape or its form. But the question is about the derivative term, okay? So in the derivative term, the transformation looks like this. So I have the derivative acting on the field, right? And then I perform the transformation, and the field transforms into the original, the field with the argument being, the space-time argument being changed, okay? And the way I can write that is by, or the way that I can formulate that is by also performing a transformation on the four derivative there, okay? And because the four derivative is a covariant vector, it's being transformed with the inverse of the Lorentz transformation, okay? So the transformation of this derivative term looks something like this. So it's just basically the transformation of the index of the four derivative, okay? I was confused by my own notes for a while because the term on the far right, the lambda minus 1x, that's just the argument. Okay, I'm just saying that the argument of that stuff is, I couldn't figure out for the life of me where that was coming from. And then I realized that it's just the argument. Okay. All right, so that's how the derivative term transforms. And now what we want to do is compute how the kinetic term for the Lagrangian computes, right? How this del mu phi squared, right? And in order to do that, we can actually use a relationship that I think we've derived several times, which is in terms of the metric tensor, right? So I think we've seen this identity several times, right? And actually you can write it like this, or you can write the inverse version of it, right? Notice that the indices get flip-flopped, so the ones that are down go up and the ones that are up go down, right? Well, let's see how I use that, okay? So let me try this transformation of the kinetic term, all right? So first, I'm going to pull out a g mu nu and write both of the indices down. All are both, that's both of the indices, they should be both up. Right. So they should both be both up, okay, on the derivative terms. Okay? And then I perform the transformation, right? That gives me the 5 primes. And then the 5 primes I rewrite in terms of that transformation that I derived earlier, right, for the derivatives, in terms of the lambda inverse. Okay? And now what I can do is the lambda inverse, they can pass through those derivative terms, right? And so I get something up there that looks like G mu nu times 2 inverse of these Lorentz transformations. Okay? And that's just equivalent to another metric tensor, right, with the indices changed. Okay? And so what I find is I get the metric tensor being divided into 2 derivative terms, and that I can, group together as del mu phi squared. Okay? Everybody following?
I guess G mu equals do this.
The what?
The G mu.
Mm-hmm.
Should be up in this.
Yeah, that's what I was saying. That in this first line, is there like a stick or anything in here? Okay.
Just that's use your mouse for this.
Yeah. Yeah, that's right. Okay. Yeah. So right here, this is a typo or I guess a righto since I wrote it, but it's the indices should be up on these terms.
You could take the index of the metric tensor.
Yeah, but yeah, it's the same. Either or. Oh, you're saying because I want to use this identity up here? Yeah. Yeah, you can do that. It doesn't matter. They're being dotted into each other, so it's okay. All right. So yeah. So if you want, you can change this and make the indices of the metric tensor be up. Okay. And then you can use this identity up here. Okay. But the important point is that I go through this transformation, right, and I get back something that looks exactly the same. Okay, it's just added the new space-time point, right? So in other words, what I find is if I put it all back together after the Lorentz transformation, I get back a Lagrangian that looks exactly like what we had before, this thing. Okay, the difference being that it's now at some new space-time point, but the equation is the same, the form of the equation. Okay, so the whole Lagrangian transforms as a scalar, which we've established a couple of times now. Okay, and if the Lagrangian's a scalar or Lorentz invariant, then you know the Klein-Gordon or the equation of motion is also going to be a Lorentz invariant. Okay. Okay, so that's all old news. All right. What I want to start to talk about now is the case where your field not only has it's not just valued, but it has a direction, right? It has so like a vector field, right? So like a a field that has a direction. Okay. And not only the vector fields, but we'll talk about other examples of multi-component fields and how those transform. Okay, but the prime example of vector fields that we've seen already are the 4 current density and the vector potential, and we'll talk about how we quantize those later. Right? But in this case, when I perform my Lorentz transformation in field space, notice now that a field not only has a distribution and it has some maxima, but it's got a direction. Right? That's what that arrow is denoting. So as I perform my Lorentz transformation, right, it's going to be some combination of boosts and rotations, right, of the field. Right? I have to make sure that I'm rotating the direction of the vector, right? So that means that the components of that vector are going to change. If you want to think about it in terms of like, just normal 3-dimensional Euclidean space, right? And in fact, when we talk about a vector field, which I would denote by this V mu here, you can actually use the analogy of 3-dimensional rotations, right? So 3-dimensional rotations, You represent it by some matrix R, right? Rij, right? And it operates on the vector, right? And that at the same time, the components of your vector are changing, right? As you rotate a vector, the components change. Okay. So from using just direct analogy, you can write down a Lorentz transformation of a vector field. Okay. So you can write a 4-vector. Well, this is just not necessarily a vector field, but this is just a 4-vector, right? And so you can write down how a 4-vector transforms under a Lorentz transformation. Right? The only difference is now we're going from 3-dimensional Euclidean space to 4-dimensional Minkowski space. But the form of the transformation follows through. Okay. Okay. Right. And it turns out that you can have tensors of any rank. Right. I could have a 142 rank tensor. Okay. And if I want to do a Lorentz transformation, all I have to do is basically transform each of the indices. Right. So I would just have to multiply that 142 rank tensor by 142 Lorentz transformation matrices. Okay. All right.
If we run out of Greek letters.
Huh?
If we run out of Greek letters.
Yeah. Well, that's what the ... means. Okay. And it turns out that if you want to talk about Lorentz invariance of vector fields, right, or equations that have to do with the equations that depend on vector fields, right? It turns out that any equation in which each term has the same set of uncontracted indices is automatically Lorentz invariant, right? So in other words, in Brownsville, if I write on the board really big, do you think you could see it?
Let's find out.
Okay. All right. So one example would be Maxwell's equations, right? So here I would have something that looks like this. Can you see that?
Because it's not zoomed in enough.
Yeah, it's blurred, but yeah. What it says F is equal to 0?
It's del mu acting on F mu nu equals 0, where F mu nu is this.
Not really see
You can't see it?
So you couldn't see the del.
Oh, okay.
not
Yeah, it's okay. But what I'm saying is that if you can look at an equation, and if each term has the same uncontracted index or indices, then that equation is automatically Lorentz invariant. Okay? You know, equation, if all the indices are contracted, that means it's a scalar, and so that's Lorentz invariant. But you can show that using these transformation laws and some of the other identities, that any equation that has open index, as long as each term in that equation has the same open index, it will be Lorentz invariant. Okay?
So that would not be.
So this would be Lorentz invariant. It is Lorentz invariant. It's Maxwell's equations. See, because these are contracted. And say, for example, if I added in another term, which would be, this is completely made up, but whatever. If I had some vector v mu, if I just added to this some vector v mu, right?
Okay. So
Then,
now all of them will have a new.
yeah, so they all have new open, right? So that means, so this means you could represent this thing as a 4-vector, right? And how 4 vectors transform, okay? All right, so that was just a side note. I just wanted to make that point, okay? And so you can, build up theories after theory after theory, or, equations after equations, using higher order tensors and so on and so forth, right? Because you know how they transform. They just transform, the indices just transform like 4 vectors, okay? Okay, so what I want to do now is consider the case where you have some object, okay, that we can write using indices. So these indices are going to correspond to maybe components of the field, right? So maybe like a vector of fields, right? That we've taught. You guys know what I'm talking about? Okay, with phi A. So remember we had phi A, and A denoted we had in fields, right? And we denoted those with the index A. Okay. So what I want to ask is, how does an in component field like this transform? Okay. What I'm shooting for is our spinor fields. Okay. Spinor fields have an index, spinor index, right? And it's either up or down. Right, so there's two cases. But we could talk about, a spin 1 field or something like that. Okay? So that's the type of index I'm talking about. So it's not a Lorentz index. Okay? So it's not going to transform like a 4 vector. All right, that's what I want to investigate, is how a field like this transforms, right? Because you can't multiply it, you can't hit it with a Lorentz transformation matrix because it has no Lorentz indices. All right. So this shows an example right here. Okay. So I have a field phi A, depends on some space-time point x, right? And I want to perform a Lorentz transformation. Right? And the way that I do that is I build matrices out of the Lorentz transformations. Okay. So the Lorentz transformations, will be, so these matrices depend on the Lorentz transformations. Okay? So this is how I would perform this Lorentz transformation, and I know that the space-time argument, I know how that transforms. Okay? So what we want to try to do is understand the form, what do these matrices look like, right? And we're going to focus on, in particular, the case of spin 1/2, but I think we'll see some other examples along the way. Okay, so instead of having to write these indices, I'll probably most of the time just write it like this, where phi goes to m phi. Okay. All right. So, what are the possible forms of these matrices? Okay. Well, it turns out that one of the major restrictions on the form of these matrices comes from the fact that Lorentz transformations form a group. Okay. That means that if I perform one Lorentz transformation, call it lambda, and then I perform another Lorentz transformation, lambda prime, that's equivalent to just one Lorentz transformation, right? That I could call lambda double prime, right? And that's basically the definition of a group, all right? It's one of the requirements, okay? So what that means for us is that there has to be kind of a one-to-one correspondence, right? So if we can do that with the Lorentz transformations, so lambda prime equals lambda double prime, that means that when I perform two transformations on this other field, right, that we have to transform using these matrices, that the matrices obey the same type of behavior, okay? So that if I perform a Lorentz boost or a Lorentz rotation or transformation, lambda and then lambda prime, and I do that through these matrices, then it's equivalent to just one matrix built out of this equivalent Lorentz transformation, lambda double prime. Okay. And it's just the fancy way of saying is that the correspondence between these two things has to be preserved under multiplication. Okay. All right. And I don't. You guys know I don't like to delve too deeply into mathematical terms and whatnot, but this is kind of an important one that we use in the business. Okay, so we say that these matrices that we build out of the Lorentz transformations. Remember, these are in general right now they're just n by n matrices, right? Because our field has n components, little n components. So we say that this thing forms an n-dimensional representation of the Lorentz group. Okay, so the Lorentz group is that group I was talking about before, where you can perform, several Lorentz transformations and still get it's equivalent to one Lorentz transformation. Okay, so this one particular case is a representation of the Lorentz group. So what we're trying to ask is, or what we're trying to answer is, what's the possible form of these matrices, right? These M of lambdas, right? So you can rephrase that question once you have said that this thing is a representation of the Lorentz group, and you can ask, what's the, what are the matrix representations of the Lorentz group? Right? It's the same question, just phrased differently. Okay, and we're always going to consider finite dimensional. I don't even know how to think about infinite dimensional matrix representations. Okay. All right, so we want to do that for the Lorentz group, but we can actually learn a lot by first, taking a step back and considering the rotation group that you're used to in 3 dimensions. Okay. All right, and this group has representations of every dimensionality, right? So you remember you're doing rotations, but you can always, think of the rotations in 2, 3, 4, 5, however many dimensions, right? And the dimensionality of these rotations, at least in quantum mechanics, we can always relate to spin, right? So we're always interested in what happens to the spin, right, as we perform some rotation, okay? Right, and we always link those rotations to angular momentum. You guys remember this? Okay, all right. So in this case, in this special case, the n that determines the dimension of our field or of our matrices, right, goes as 2 times the spin plus 1. Right. So for an electron, for a spin 1/2 particle, you get 2. Right. So you have a 2 by 2 matrix, right, that performs the transformation on your 2-component spinner. Okay. Right. And you learn in quantum mechanics that the way that you represent these types of rotations is through a unitary matrix, right? And the unitary matrix is 2 by 2. We've already established that. It has to have a determinant of 1, right? And typically what you do is you build it up, right? You start with an infinitesimal transformation, and then you compound a bunch of infinitesimal ones. And when you sum those up, you get an exponential. Right? You exponentiate the transformation, okay? And so in this case, the transformation would look something like this, right? Where for a spin 1/2 case, we're rotating by some parameter theta, right? And the rotation matrices themselves, or the generators of rotation, are the Pauli matrices. Okay, so hopefully this is, clearing out some of the cobwebs, and it's starting to sound a little familiar. Okay, all right. And one of the things we're particularly interested in when we talk about these types of transformations are transformations that lie infinitesimally close to the identity. Okay. In other words, it's what I was saying. We always start with infinitesimal transformations, right? We talk about transformations that are continuously connected to the identity operator, right? That's how we start. Okay. And these types of transformations define what we're going to call a vector space. They form a vector space, and this vector space is what we call the Lie algebra of the group. I'll talk about more about the Lie algebra in just a second. And the basis vectors that span this vector space are the generators. All right, the generators of the Lie algebra or the group. Okay, and so in this case, our vector space is spinor space, right? And the generators that span the space are basically the Pauli matrices. Okay. All right. Okay, and so you've seen several times that for a rotation group in general, so the rotation in 3 dimensions, right? Just a normal rotation of a vector or a state ket in quantum mechanics. The generators in that case are the angular momentum operators, right? those are the guys that generate the rotations. Right? You go through this art. I don't know if you guys remember, but we went through this argument where we built up, this rotation operator. I don't know what we called it. But we called it a rotation operator, and then through kind of dimensional analysis, we reasoned that the generator, we reasoned that from units as well as from the classical idea that the generator of rotations is angular momentum, right? Okay. All right. So the same thing carries over here. All right. And so these angular momentum operators usually show either by using the classical definition of angular momentum, or you can prove it other ways. But these guys typically obey a very specific type of commutation relation. Right? So it's just like in the case of, it is the case of rotations. Okay, and so that should be a very familiar looking commutation relation. Right. All right. So here,
Oh, never mind. Sorry.
What?
Oh, for a second, it looked like the image had frozen.
Uh,
I was just
maybe they're just sitting really still. Okay, so here's what I was talking about, right? So we build up a rotation. So let me build up a rotation matrix, okay? And we start with an infinitesimal transformation, right? Or an infinitesimal rotation in this case, right? So in an infinitesimal case, you start with the identity matrix, right? And then you add on some piece that has a small parameter. In this case, it's theta, some small angle that you're performing the rotation. And then you have some operator that actually generates the rotation, right? And that's why we call it the generators. Okay? And you can actually build up an infinitesimal transformation by compounding a bunch of these. Right? And when you take the limit of n goes to infinity, the number of transformations, you get an exponential operator. Okay? In this case, like we said, in the spin 1/2 case, the j is just given by the Pauli matrices divided by 2. Oops. Just try to remember this. Yeah, this is just kind of restating everything I've just said. Right, and because of the commutation relations here and the way that those generators are related to the rotation matrices, it determines the multiplication laws for the rotation matrices themselves. Okay, so if we're going back to remember what we're trying to do is to understand what form these matrices and Lorentz transformations can take. Okay, and so what we're seeing is that the generators of the transformation determine the multiplication laws of the matrices. Okay, so in our case, what we're saying that if we were using direct analogy, we would say that the Lorentz transformation, how those guys, how they commute or don't commute, right, determines how the matrices M, how those matrices are multiplicated. Okay. Okay, and so you can carry this out for any general continuous groups, right? So in quantum mechanics, you study what's it called? Not only rotations, but translation, right? So linear translation, right? There, the generators are linear momentum, okay? Right, so for any type of continuous group or continuous type of transformation, you can go through and do all this stuff that we just talked about, right? And typically what you do when you do that is you start by finding matrix representations of the generators, right? And these guys have to satisfy certain commutation relations, right? And then you can build up the matrices that depend on those generators through starting with an infinitesimal transformation and then building them up by compounding a bunch of infinitesimal transformations. Okay. All right, so what we need to determine for our case, right, which is the Lorentz group, is we need to know the commutation relations of the generators for this group. All right, so first we have to determine what the generators are of the Lorentz group, and then we can try to figure out what their commutation relations are. Okay, so the first thing that you would do in the three-dimensional case, the three-dimensional rotation case, is you would first define the generator, right? You have to compute the generator itself. And like I said, in undergrad quantum, you learn how to do this. You just basically promote the classical angular momentum to an operator. Right? And classical angular momentum, is x cross p, right? Or in the quantum case, it's x cross del. And then you would take that guy and you plug it in. You can compute the commutator between, say, Ji and Jj. Okay. Two components of the J vector. All right. But what we're trying to do is make an analogy here to our Lorentz group case. Okay. So let me take the J vector there and write it in notation that will be easier to generalize. So I'm going to write Jij, which is going to correspond. So if it was, say, J12, that corresponds to J3. J3 being rotation about the z-axis. Okay? All right.
Does star mean anything?
Oh, no, that's just my notation for, a little side note. Yeah. Sorry. These weren't meant for public consumption. These are my handwritten notes. But as I was saying at the beginning of class, I'm just going to project these instead of writing. So you might see notes. There might be notes to myself in these things. Okay. So just disregard those if you see anything like that. Okay.
And that minus I coefficient is imaginary.
Yes. Yeah. So don't get the I out in front confused with the ij indices. The I out in front is square root of -1. Okay. All right.
Yeah.
Okay.
Confused me at first, but I figured, but now I thought.
You just at some point you run out of letters. Okay. Letters. Okay. All right. So what I want to do is I can use that, and now I can generalize this, just like we did when we were talking about 4 vectors. I can generalize this tensor to Minkowski space, right? By just changing the i's and j's to mu's and nu's, right?
Well, that gets rid of our I confusion.
Huh?
That gets rid of our I confusion.
Yeah. It would have really blown your mind if I had mu out in front. Yeah, you have a question?
Question, yeah. When we have 3 vectors, we know that J12 is J3, J21 is minus J3. But when we have 4 vectors, when mu equals to 1 and mu equals to 2, what is it equals to?
It will still be J3. Right, because that's going to be
J13, what is it?
No, it would be equivalent to a rotation about the z-axis. Right, remember,
A rotation around time axis is boost, right?
Yeah, no, well, so the 0, so if you set mu nu to 0I, right, those are the boosts. Right? And if I had mu nu equal to ij, those are the rotations, right? But they're the 3 vector rotations. So J12 would still correspond to a rotation about the z-axis.
And J01?
And J01 would correspond to a boost along the x direction.
Okay.
Make sense?
Yeah.
Okay. But good question. Okay, so this right now, the way I've written it down, it's not necessarily, I'm just using an analogy, but maybe the J there is a little confusing because this isn't just rotations now. It includes boosts. Okay, so you might have seen this written with a different letter, say in Jackson or some other book. Okay, but we're going to use J because we want to use this analogy of angular momentum. Okay, and so you can show that this thing has it's basically 6 operators, 6 independent operators. 3 of them are boosts, and 3 of them are rotations. Okay. All right. I don't want to blow your mind yet. Okay. So, so we want to determine the commutation rules. Okay. And typically, what we would do is, in the 3-dimensional case, we just feed them into a commutator and we compute, and whatever comes out comes out. Okay. So in this case, in the Lorentz case, right, we would do the same thing. We would take these transformation matrices and we compute the commutator, right? And it comes out to be a mess, okay? There are a lot of terms there, but this is, the equivalent of what you would write down for, or it's, the analogy of what you would write down for angular momentum, right? It defines the Lie group, or the Lie algebra of the Lorentz group, okay? And you're going to have some fun with this on probably multiple homework assignments. All right. So if we want to build up a matrix, right? Remember, we're after the form of matrices that kind of, perform Lorentz transformations on things that aren't 4 vectors or things that aren't scalars, basically, right? Things that don't have Lorentz indices. Okay, but if you so now that we have the generators, right? So these guys are the generators, the J mu nus, and now we know how they commute or don't commute, right? Now we can from what we said before, that determines how the matrices themselves built out of these generators are multiplied. Okay. And so, in other words, in any matrices that are to represent this algebra, they have to obey the same commutation relations. Okay, that's just coming from the definition of a group. Remember, we talked about two transformations corresponding to 2 matrices of transformations. Okay, so it just okay. All right, so. So let's look at one particular type of representation or one type of transformation, okay? And this thing is kind of ugly looking, but let me explain what it is. So it's a generator, okay? And you can build matrices, or you can build the matrix form of this thing. The way it works is it's a little confusing because the mu, nu, and alpha, beta. So mu and nu label which of the 6 matrices you want, right? So they would either be like 0, 1, 0, 2, 0, 3, or 1, 2, 1, 3, or 2, 3. Okay? That's what you would set mu and nu to. Alpha and beta actually label the components of the matrix. Okay? So those would be the row and column components. Okay? It's just an unfortunate notation. Okay? And you can show through explicit calculation that these guys obey this commutation relation. Okay, so when I take this funky looking, what do we decide that this is a T? This T mu nu alpha beta, right? And I feed it in here for the J mu nus, that these guys will obey this commutation relation. Okay? And that'll be a homework problem because it's a good one. Yeah, yeah. So you see, I mean, I used to be really hard, man. I gave really hard homeworks and a lot of homework, apparently. But the way to do this, I'll just tell you right now, the way to do this problem, I mean, you can do it using the shorthand notation here with the Kronecker deltas, but maybe the easiest way is to just construct the matrices themselves. Okay? I'll just leave it at that. All right. And when you do have this problem, I'll remind you again, but you don't have to show it for every possible combination. Just show it for like one boost and run, one rotation, two boosts, two rotations. All right. So-
Does it mean that alpha and beta is row and column of this matrix, and mu and mu it's actually number for operator, right?
Exactly. Yeah. Yeah. It's just it's like I said, it's unfortunate notation. Huh?
Like it's hard to make four-dimensional matrix. It won't be matrix anymore.
Yeah, no. It's those just label mu and nu just label if you're talking about the boost or a rotation. Alpha and beta are the row and column. Okay, so think about it. So I wish I could do it on the board. So if I wanted, let's say I wanted to build the boost along the x direction. Okay, I want to build the matrix that corresponds to that. All right, so I would set mu equal to 0, nu equal to 1. Okay, and I do that on both sides. Okay, and then I go component by component. Right, so I would say my 0, 0 component, or yeah, I guess you would do 0, 0 component, right? And you would, for alpha and beta, you plug in 0, right? And those Kronecker deltas will either give you 1 or they'll give you 0, right? So you'll have most of the components will just give you 0, but every once in a while you're going to have some that give you non-zero values. Okay? That makes sense? Okay. So like I said, the easiest thing to do, I mean, I've seen it done where you can prove it using these, using the Kronecker delta form of it, and plugging that in here. But it gets really confusing really quick because you've got so many different indices to deal with. Okay? That's why I say when you get to that homework problem, build the matrices. Okay?
But it's just generators. If I want to find Lorentz transformation from these matrices, I need to multiply it by what? By speed. If, for example, I wrote down my boost along x-axis, after that I need to multiply by speed and find the exponent of it, or how can I find Lorentz matrix, the Lorentz transformation from this matrix?
Well, that's what I was saying, that you would set mu and nu. So for your boost along the x direction, you set mu and nu equal to 0 and 1. Right? And then I would go.
He's saying, once you've made that matrix.
Yeah.
No, but it just once. I will get matrix with zeros and ones. And
Right.
how to get actual Lorentz transformation from that?
Well, that would be your generator. Yeah. So you would multiply it by some parameter, right? Yeah.
I mean,
Yeah, if
I
you're
don't
talking-
understand how I get gamma from this. But all these gammas and betas.
Oh, right. Yeah. Yeah, that's what I'm saying. That you have to This is just the generator, right? If you look back at the form of this, let's go back to this rotation, right? This guy, right? This R, right? So you would build up the same thing. So J here would correspond to that thing that you just built, right? And you have to multiply that for it to be a boost. You have to multiply by some parameter, right? And in the case,
What is this parameter?
Yeah, I don't remember. It's the I do remember. It's the pseudo rapidity. Eta.
What?
Yeah. Go back, look at Jackson. I think it's chapter 11 or 12. It's the boost parameter is eta. It's called the pseudo rapidity. Never heard of it?
Sometimes it's
No.
called,
Okay.
sometimes it's called gamma.
I know I've seen it several times about running stuff.
I don't know. I mean, that's the parameter that you multiply by. Now, its relation to beta and gamma, I don't remember that. But I do remember that the boost parameter, which is what we're talking about in this case, is called eta. Okay? It's a pseudo rapidity.
And that operates on.
It's the quantity that's additive under successive boosts. That is drilled into my brain.
So one of the things you mentioned, like in the part, the
Yeah.
tech,
Yeah. But in more general terms, in more general terms, it's the parameter of the boost. Take my word for it. All right. I mean, look it up in Jackson and tell me if I'm wrong, but that's what's drilled into my brain. That's what coming to mind.
That's something that'll train you on the job.
Huh?
They'll train you on the job.
Yeah. All right. So let me find where I was. Okay. So I was talking about this guy, and we said that you could actually show, and you will show that it obeys the commutation relation. All right. And it turns out that this guy, you'll find, is nothing more than the generator of boost or rotations that acts on 4 vectors. Okay. So in other words, if I wanted to transform a 4 vector, I would do it like this. Okay, under a Lorentz transformation, an infinitesimal Lorentz transformation. All right. So you see the first term is basically the identity matrix, or it's a identity. Yeah, it's like the identity matrix. Okay. And you see at the end, I have my generator, that T mu nu alpha beta, right, being contracted on some 4 vector. And then I have some parameter, omega mu nu. Okay. And I put indices on there because this thing has to be anti-symmetric. And why? You might know why it has to be anti-symmetric. Why? You might know why this has to be anti-symmetric. The omega mu nu.
Because T is anti-symmetric.
Because when we find product of symmetric and anti-symmetric tensors, no, it's actually we don't find convolution.
Anti-symmetric in order to get another symmetric term. T is
So you're saying T is anti-symmetric?
We have some over mu here.
Yeah.
Oh yeah, we have some over mu and then when we have convolution of symmetric and anti-symmetric tensor, we'll get 0.
Yeah. Yeah. So that's exactly. I didn't know. I was asking. No, I'm just kidding. I knew, but yeah, that's the reason, right? Because T mu nu, if you look up here, is anti-symmetric, right? Under the exchange of alpha and beta, and so you need this guy to be anti-symmetric. Okay.
No, actually it cannot, but we just don't care about symmetric part. it won't give us anything. It will give us 0. It doesn't change anything.
Yeah, I think it's equivalent, right? I don't know. Okay. All right, so let's consider a specific case to see how this works. All right. So I'm going to take omega 1, 2 to be some angle. Right. So that means I'm doing some rotation, right? And all the other omega ij's are 0. And so what I can do is actually construct the matrix, this matrix that would operate on a 4 vector, right? And it would look like that, right? It looks just like, if you considered the 3 by 3 kind of submatrix here, it's like a rotation about the, what are we doing? 1, 2, it'd be a rotation about the z-axis, which is not, let's see, what sub, this would be 0, 1, 2.
If you're calling it 0, row 0, column 0.
Mm-hmm. This would be omega 1, 2, omega 1, 2, but this to me looks like, am I reading this wrong? This to me looks like it's a rotation about the y-axis. If I look at that matrix. Rotation in the xy plane. So this would be time x, y. Okay, maybe I'm just thinking of it.
the first row is
0.
the boost. Yeah.
Yeah, so these are the boosts the top row and the first column are the boosts.
Is the component is yeah.
Yeah, I would say the Z component is this guy. So that's what's confusing me about why it's appearing here and not in the Z component.
We have rotation around Z. Z component doesn't change. It's just X and Y.
Yeah, that's right. Yeah. Okay, thanks. Long day. Right, and so another example would be a boost. Right, so you could build up the matrix that operates on a 4-vector by taking, say, omega 0, 1, and to be some beta, right, some parameter beta. And in that case, your matrix would look something like this. Right, and that's obviously a boost in the x direction. Right, and so what you find is that these guys, like I said, there's 6 of these, 6 independent. There's 3 boosts and 3 rotations. And what the hell is that? And those are the actual, those are it's the actual generator of these 3 boosts and 3 rotations of the Lorentz group, right? For a 4-vector. Okay. All right. So what I want to do now is apply this to the case of spin 1/2 particles, right? To try to develop the Lorentz group for spin 1/2. Okay. So let me pull it up real quick. Okay. All right. So now what we want to try to do is apply what we just learned to the case of spin 1/2. Okay. So our goal here is to find the representation of the Lorentz group corresponding to spin 1/2. And once we've done that, that'll tell us basically how we can write down the equation of motion or the Lagrangian for a spin 1/2 field. Okay. Okay. All right. So we just derived one particular finite dimensional representation of the Lorentz group, right? And you could keep going on like this, right? You could derive the Lorentz transformation group for different tensors and whatnot. Okay. But what we want to do now is just focus on spin 1/2 case. Okay. And we all know, it's no surprise, right, that we already know of a Lorentz invariant equation for spin 1/2 particles. It's the Dirac equation, right? And so, just to remind you, a little refresher on the Dirac equation, right? So Dirac's equation was born out of trying to write down a fully relativistic, relativistically invariant Schrodinger equation for the spin 1/2 particle, in particular for electrons, right? And for a fully relativistic case, the Schrodinger equation looks like this, right? Where I've set h bars and c's to 1, right? And Dirac's idea was that maybe that stuff inside the square root you can write in such a way that it's a perfect square, right? So that way I can take the square root. And so he showed that, that you could do that, but the right-hand side would have to be, some operator built out of momentum, but having these objects alpha and beta. I don't know how much longer I'm able to go on. My voice is going. And this he named after himself, the Dirac. No, I'm just kidding. I don't think he named that for himself, but it's the Dirac equation. Okay, the me equation. Yeah. But the thing to notice is that you can tell that it's Lorentz invariant because it treats time and space on equal footing. Right. On the left-hand side, time is linear, and on the right-hand side, space is linear. Right, in the form of the momentum operator. Okay. And through different exercises, you can ask yourself, what do we know or what can we figure out about these alpha and beta things, right? And you find that they have to be space independent, right? Because they have to be able to pass through this derivative here coming from the momentum operator, right? And you find that they have to be Hermitian, which is not surprising because you're talking about the Hamiltonian basically, right? And they have to satisfy certain anti-commutation relations, right? So in order for that thing, right, when you square it, in order for it to give you minus del squared plus m squared, right, these conditions have to be fulfilled. So the square of alpha and the square of beta have to be 1. Right? And note that there are 3 alphas and 1 beta. Okay? And they also have to obey certain anti-commutation relations. Right? So they have to anti-commutate. There's other things you can deduce. One is that they're traceless and that they have eigenvalues of plus or minus 1. Right? And that implies that these things have to be even dimensional. Right? Because the only way you can get traceless out of eigenvalues plus or minus 1 is if you have equal numbers of pluses and minuses. Okay? The problem is that, when you're talking about this in quantum mechanics, this all sounds fine and good. When you look at these anti-commutation relations, you're reminded of, certain, and these other conditions, you're reminded of a certain group of matrices that obey these same rules, and they're the Pauli matrices, right? So you think, okay, I'm good to go. But the problem is that you need 4 matrices, right? You need 3 alphas and 1 beta, and there's only 3 Pauli matrices, right? And those span that vector space. So you can't add on a 4th Pauli matrix, okay? So you're forced to kind of go to higher, what do I want to say, to a higher dimensionality for the spinner, right? So the Pauli matrices are 2 by 2, which tells you your spinner has to be 2 component, right? Spin up, spin down, right? But these rules are telling us that, we can't just have the Pauli matrices, we have to have an extra one, right? And they also tell us that these matrices have to be even dimensional, right? So the next possible choice would be 4 by 4, okay? Let's see. Right, and so what this leads us to is a 4-component Dirac spinner, right? And you interpret the top 2 components as being, your positive energy states, your spin up and spin down, while the bottom 2 of the Dirac spinner turn out to be negative energy states, right? And that was a problem in the beginning, but Dirac said, no, it's no problem. Just imagine that there's a sea of negative energy states, but they're all filled, right? They're all filled, and so by the Pauli exclusion principle, you can't have electrons, positive energy electrons, giving off photons and diving down into negative energies, okay? Because the Pauli exclusion principle excludes that possibility, right? And so, from this, and he made other important. Maybe the most important thing was that if you were able to actually knock out one of these negative energy electrons out of the sea, right? That hole that remains, though you have a hole there, that hole to us would correspond to what we would call an antiparticle, right? So it would look exactly like the electron. It would have the same mass, but the only thing different would be it'd have opposite charge. Okay, and so he predicted that using this crazy idea of this infinite sea of negative energy electrons, and it turned out to be right. Right, at least a few years later they found the positron, right, and so they thought he was onto something. Mm-hmm. Yeah.
Is it only about the charge? So was it the only thing, the different electron in the positive energy state and negative energy state is just a charge?
Well, we also have opposite lepton numbers.
Why this? We have particle or even field of particles, right?
Yeah.
And some of these particles, they have negative energy.
Right.
Or
well, that was the I mean, that's what the solution looked like. It looked like it was giving you negative energy states, right? But they're electrons with negative energy states. Okay, so it's all describing electrons. But what he said was, if you had a photon come along and smack one of these negative energy states and knock it up to a positive energy, right? What would be left inside that sea of negative energy electrons would be a hole, right? And he showed that hole, if we were to observe that hole, to us it would look like a positively charged electron. So it'd have opposite charge of the electron. But in the theory itself, they're all electrons. It's just that some are positive energy and some are negative energy.
But it means that electron with negative energy, they always exist.
What was that? I'm sorry.
Electrons, I was assuming it would have Dirac equation that describes some fields, and particle of this field is electron. Is it correct? Or, for example, for any kind of field, phi, right? We can say that different. Can we actually introduce the number operator for this field and say how many particles they will have for our phi in the Dirac equation?
Yeah, that's the way we'll do it. I mean, we'll quantize it using the same approach. So based on second quantization or the simple harmonic oscillator kind of analog, yeah.
Assume that I have zero energy, but if I have a limited number of electrons with negative energies, what should my number operator show? Zero?
Oh, yeah, I got you. Yeah, so it's a tricky question, right? So it turns out that interpretation is wrong, right? But it was an effective, it's what we call an effective theory. So it effectively, predicted the positron, the existence of the positron. But later on, we realized that relativistic quantum mechanics just doesn't work, right? And you have to go to quantum field theory. Okay. All right. I think I'm just gonna stop there because my voice is about to go, and that kind of leaves us off right at, so relativistic quantum mechanics is garbage. No, I'm just kidding. It's not garbage, but it doesn't work. Right. So that tells us that we have to go to field theory. Okay. And so we'll develop a field theory for Dirac particles. Okay. Or Dirac objects. Okay. All right. So we'll do that next time. I don't think I put a due date on that homework, but let's just say it's kind of long. So maybe not next Wednesday, but the Monday after that. So a week and a half.
Okay.
Almost 2 weeks?
Yeah, almost 2 weeks. So whatever the next Monday is. Okay.
He didn't say it was hard. He said it was long.
Yeah, it's long, from what I remember. Okay, but just let me know if you have questions about anything. Let me know. Okay.
All right.
I think. Oh, the other thing is, in problem 1, it makes reference to some set of notes. I'll put those notes in the Dropbox. Okay. All right. Have a good weekend. Thanks again, Terry.